Hello students, good afternoon. Who all are there, please type in your name in the comment box. Hello students, good afternoon. Please join the link guys, I have shared on the group. And mark your attendance in the comment box, all of you please. Hello Shreya, Samyukta, Ardra. Where are others? Guys, please join fast. Did you solve the assignment that I have shared on solution chapter? All of you have done that? Okay. Okay, let them join. So, guys, today we are going to start a new chapter of inorganic chemistry, and the chapter is coordination compound. Okay, we are going to discuss this chapter today. First of all, you see what is a coordination compound. Like we know about the normal compounds we have, that is NaCl, NgCl2, etc. These are simple compounds. Okay, and we have only one kind of bonding in this kind of compounds, right? The major difference between coordination compound and the simple compound is the type of bonding which is present in coordination compound. Okay, coordination compound, mainly there are two types of valency we have, two types of bonding we can explain by different theory. But in the coordination compound, we have two types of valencies. Okay, so don't write it just now. Just let me explain, or let me give you a brief idea of this chapter and what is this compound is all about. In coordination compound, there are two types of bond present or valency we have. The first is primary valency, and the first one is primary valency, and the second one is secondary valency, right? Generally in the compounds we have only one type of valency present. Okay, hello Paras. correct? But in coordination compound, we have two types of valency. These coordination compounds have different properties also, right? Properties in the term when we dissolve this into any solvent like water, correct? So what happens when we dissolve a coordination compound into water? The way of dissolving these compounds into any solvent, that is also different from the various simple compounds that we have. Okay, and we have a huge application of this coordination compound in our day-to-day life. First of all, if I give you some examples like chlorophyll, okay, chlorophyll found in plants. This chlorophyll is a complex of magnesium, okay, Mg complex, complex of magnesium. Okay, if you talk about hemoglobin, right, HAE, hemoglobin, these are the complex of iron, iron complex, which is very useful, right? Blood hemoglobin is observed is found in blood. Chlorophyll is found in plants. Magnesium complex. So with all these examples, you can see this has a huge application in our day-to-day life also. Okay. Now the main thing is what here you have to understand before going into the classification of compounds. Suppose if I take one example of coordination compound, which is K4FeCN6. Complex of iron K4FeCN6. Okay, this is a coordination compound, and we also call it as complex compound. Coordination compound or complex compound are same thing. Okay, both are same thing. Correct. Now there are various terms involved in this particular type of compound. That term we'll see. Okay, but the major difference is what? Suppose if you have any simple compound, like I say, we have NaCl. One example I am taking of simple compound NaCl. When you dissolve this into water, H2O, it dissolves into two ions, that is Na plus and Cl minus, and those ions we call it as Na plus aqueous and Cl minus aqueous. Okay, and what we say, since this ion or this molecule dissolves completely into its ions, so what we say that these simple compounds loses its identity into solution. Identity in solution. Losing identity means what? It dissolves completely into its ions. Okay, the ions from which they have formed, it dissolves completely into those ions. So NaCl is no longer is not existing in the solution. It exists in the form of what? Na plus and Cl minus. Hence we say that they loses their identity completely. I'm talking about normal compounds. Okay, but these coordination compound, if you dissolve this into water, this also dissociates into its ion form, but the dissociation is not complete. Okay, like suppose this molecule dissociates in the form of this, we'll get 4K plus, and the another ion will be FeCN6 4 minus. These are the two ions we get. Understood? These are the two ions we get. So what we observe here, that this ion, it won't dissociate in the form of K plus, Fe plus, Cn6, Cn minus. This kind of dissociation won't be there. But it dissociates in the forms of K plus and this complete thing, negative charge on it. Okay? So what happens here, you see, this part, which is the complex part, the part or the, which is written in this square bracket, we call it as the complex part of this compound. Okay, this is what? This is the complex part. So when you look at this ion, complex part, when you look at this ion, the complex part does not dissolve. It retains its identity in the solution. Okay, because there is no Fe plus and Fe minus and Fe plus and Cn minus present, but this whole ion is present, in which FeCN bonding still exists in the solution. Okay, so what we say, the complex part retains its identity, even in the solution, retains its identity even in the solution. So this we call it as, this is the major difference between a simple compound, this is a simple compound, and a complex compound or coordination compound. This is the major difference. Simple compound dissociates completely, loses its identity completely in the solution. Here, the dissolution is not complete. The complex part retains its identity even in the solution. Do you understand the basic difference between the coordination compound and the simple compound? If you understood, please type CLR in the comment box quickly. Okay, correct. Okay. Now coming back to the next point, to understand this coordination compound, we must require the concept that we already studied, which is the concept of chemical bonding. Chemical bonding concept you must have. Concept of chemical bonding you should have. You should have the concept of no orbital overlapping. Orbital overlapping. Or you should have the concept of hybridization. These three things you must know to understand the bonding in complex compound or coordination compound. Okay, so if you have any doubt into this, please go through it after this class. Okay, because today we are not going to use this, but in the coming class obviously we'll use this concept to understand the bonding. Okay, but again we'll discuss this into the class also. Okay, now if I write down the classification of compounds, like the basic understanding I have given you, like what is a complex compound, what is a coordination compound. Two types of bonding I said, this K plus and Fe. This we call it as metals, right? This is metal, and we also call it as the central metal atom. CMA is the abbreviation we are going to use for this term, central metal atom. Okay, that this term we'll use very frequently in this chapter, central metal atom. So whenever I say central metal atom, write down CMA. Okay, this is metal, and this Cn minus is attached with this metal, and K plus also attached with this metal. This Cn minus will have a different kind of bonding with this metal. K plus will have different kind of bonding with this metal. That's why we say the bonding of K plus and Fe is different, Cn minus and Fe is different, and hence we say two types of bonding we have, which is nothing but the two types of valency we are seeing, primary and secondary. So we'll discuss this later. Okay, we'll go into detail all these things later. Okay. Now you see the next thing we have to understand is the classification of compounds. Classification of compounds. How the compounds are classified. See, there are mainly two types of compounds. Means the compounds are classified mainly into two categories, first of all. Which is, the first one is, we call it as additional compound. Copy this down. Additional compound, or we also call it as molecular compound. additional or molecular compound. The next one is simple compound. Simple compound. Simple compound, like I already told you, the examples of simple compounds are like NaCl, MgCl2, etc., which dissociates completely. These are simple compounds. Okay. Additional compound or molecular compound. Again, this is also classified into two categories. Into two categories. And these are, the first one is double salt. Double salt. And the second one is the coordination compound. The coordination compound. Okay. So double salt, the example is what? We'll see that examples of double salt. Additional or molecular compounds are those compounds which contains water molecule as in the hydrated form. For example, you see the additional compounds, examples of this you write down. Suppose if I write down the molecule like carnallite, KCl dot MgCl2 dot 6H2. This is additional or molecular compound. Water presence in the hydrated form. The name of this compound is carnallite. Name is also important. You must keep this in mind. Another example of additional compound, we have Morse salt, which is nothing but FeSO4 dot NH4 2SO4 dot 6H2O. The name of this compound is Morse salt. Right? They won't ask this name in JE, but in the other, state level exams like CT and all, they ask these things also. What is Morse salt, like that? Okay. So name is also you must keep in mind. Okay. One more compound we have, which is not that much important, but we also call it as potash alum or simply alum. The formula is K2SO4 dot Al2SO4 whole thrice dot 24H2O. All these, when water molecule present in hydrated form, we call it as alum. Right? These are additional compound. Got it? Now, additional compound, like I said, it is classified into two categories: double salt and coordination compound. Double salts are what? Just point wise you write down. These are the compounds which are stable in solid form. Stable in solid state, actually. Stable in solid state, but in water, but in water, it dissociates completely. Dissociates completely. Like, for example, you see, if I am using this, only one example I'll write down, KCl dot MgCl2 dot 6H2O. If you dissolve this in water, it dissociates completely and it forms various types of cations and anions. K plus it forms Mg2 plus, it also forms 3Cl minus, plus will have H2O as it is, 6H2O. You see, all these dissociates completely into its ion. We call it as double salt. Similar kind of nature of simple compounds also we have, but it is not the hydrated form. There is not a dot kind of structure we have, NaCl, MgCl2 like that. Okay. Coordination compounds, like I already discussed, these are the compounds which does not dissociates completely. One example you see K4FeCN6, FeCN6, and when it dissolves in water, it converts into 4K plus FeCN6 4 minus. Okay, does not dissolve completely. Understood? So for this chapter, more focus will be on this coordination compound. That is what we are going to study in this chapter. This is the brief idea of what all different types of compounds we have. Our focus will be on coordination compound. Coordination compound and complex compound are the same thing. Okay. Did you write this? Can we move on? Let me know, guys, if you're done. Okay. Next page. Now you write down the definition of coordination compound. Write down the definition first. Write down to this. These are the compounds. These are the compounds which forms by. These are the compounds forms by two or more two or more simple by sorry by the combination of by the combination of two or more simple stable compounds simple stable compounds that retains their identity retains their identity in solid as well as in dissolved state in solid as well as in dissolved state. Okay. Now you see, in this chapter, we are going to use various different terms to understand this coordination compound. Okay. So first of all, we'll see what all those terms we have. So that term we are going to understand with like one simple example, and the example is same I am taking K4 Fe CN6. K4 Fe CN6. Now you see here the the part which is written in the square bracket, we call it as the complex part, right? This is the complex part, and we also call it as complex part or coordination sphere. Okay, this is the complex part, and we also call it as coordination sphere. And instead of sphere, we also write it as coordination entity. That is also same thing, right? So coordination sphere, coordination entity is the complex part. And what is the nature of complex part? Complex part does not dissolve in solution, means it retains identity in the dissolved state, that we have already discussed, retains identity in the dissolved state. This is first term, right? The central metal atom is this, okay? This iron is the central metal atom. This is central metal atom. CMA is the central metal atom. This thing, CN here, we call it as ligands. What is ligands? That also we'll see. These are ligands. Okay? And the ion which is present outside this square bracket, we call it as ionization sphere. It is ionization sphere, or we also call it as counter ion. Both are same thing. Ionization sphere or counter ion. Understood? What is ligand? Ligand is the electron pair donor. Ligands are electron pair donor. Did you finish this chapter in the school, guys? Okay, fine. Okay, these are electron pair donor. Okay, now these are the few terms that we use for central metal atom, ligand. All these terms we'll use very often in this chapter. Okay, so you must keep this in mind. What is ligand? What is central metal atom and all? See, like I said, electron pair donor. Ligands are what? Electron pair donor. So these ligands, we have 6 ligand present here, and all these 6 ligands donates pair of electrons, not one single electron. I'm talking about a pair of electron. So one ligand donates one pair of electron to the metal. Okay, so if the ligand is donating electron to the metal, it means the metal has the ability to accommodate those electron pairs. Yes, ligands are donating electron to the metal, so metal must have the ability to accommodate those electrons. Correct? And how the metal will accommodate those electrons? For that, metal must have vacant orbital present with it. Okay, if the metal does not have vacant orbital present, they won't be able to accept those electron pair which is donating by the ligands, and hence the bond won't form. Correct? That is why we say what? That these kind of compounds, which is coordination compound, mainly forms by mainly forms by transition element. Write down, coordination compound mainly forms by mainly forms by transition element, d block elements. Why transition? Because we know in d block elements there are vacant d orbital present. So in those vacant d orbital of metal, ligand can donate its pair of electron and the bond forms. Okay, so this is the property of the ligand. Ligands are what? Ligands are the electron pair donors. Metals accept electron pair from the ligands, and hence generally we say what, that the coordination compound is mainly formed by the transition element, since they have vacant d orbital. Since they have transition elements have vacant d orbital. This is one thing. Okay. Another thing is what? You see the complex part in this example, K4FeCN6. This is positive charge. If you find out the charge on the complex part, the charge is negative, right? This is -4 on this complex part, and this is +1. 4 plus, so 4 negative here. So when the minus charge or negative charge present on the complex part, the molecule is said to be complex anion. Okay, so this molecule, not that important name, but I'm just giving you one small information here. This molecule is known as complex anion because the complex part is negative. So it is complex anion. Similarly, we can have complex cation also, and we can have complex cation, complex anion. Both possibility we have. All the three possibility basically we have. So complex anion, one example we have seen. The another example you see for complex cation, if I write down this molecule, CONH3 6 close bracket, and then we have Cl3 outside. Okay, so now in this molecule you see Cl minus will have here, so -3 on this, so here we have +3 and -1 on one chlorine atom. See, the complex part has positive charge, and hence we call it as complex cation. Complex cation. Okay, another example you see, one more I'll write down. Suppose if I write down this molecule, CONH3 6 Cr C2O4 whole thrice. Okay, so in this both cation and anionic part are complex, so we call it as complex cation, and complex anion. So basically all three possibility we have in coordination compound. We can have complex cation part, complex anion part, and both part can be complex as well. Okay, if I take this example, can you tell me this term, ionization sphere, coordination sphere, ligand, central metal atom? Can you tell me what is this cobalt here we have? What is this cobalt here? Out of this term that we have discussed here, ionization sphere, coordination sphere, ligand, central metal atom, what is this cobalt? It is central metal atom, right? So this cobalt is the central metal atom. What is NH3? What is NH3? What is NH3? Ligand, right? NH3 are ligand. What is Cl minus? What is Cl minus? Who is this MAS? Cl minus is the counter ion or ionization sphere. Okay, counter ion or ionization sphere. Okay, what is this part? This square bracket. The whole thing is what? The whole thing is coordination sphere. Acha, Aditya is MAS. Okay, right. So understood the terminology: ligand, central metal atom, ionization sphere, coordination sphere, or entity. Okay, this you must remember. Now we'll see one by one what is the definition of ligand we have and how the behavior of ligand. Right. So next thing, see guys, one thing I'll tell you: this is the only chapter in inorganic chemistry where you can apply some logic and you can understand the question. There are few things to memorize that you have to do, but to solve the questions you can do it logically. It's very important, and every year in JE they ask one question from this chapter, and you never know what question they are going to ask, because everywhere you can have possibly 10 to 12 different types of question possible. Okay, out of all the concept that we will study in this chapter, the isomerism is the most important part in this chapter. We have isomerism in coordination compound. Okay, that we'll discuss in the last, but on the basis of this isomerism concept, they ask question every year in JE exam or BITSAT or any other exam, CET, NEET, whatever you write. Okay, so this chapter going to have one definite questions from this chapter in the exam. Okay, 10 to 12 different types of question possible. So that's why it's very important to understand. Few things again you have to memorize, but that I'll say around 10 to 15% only things you have to memorize. Rest you can do it by logic. Okay, so next thing you write down the various terminology that we have seen, that is ligand and all. What is the definition of that? The most important term we have here, and that is ligand. Write down ligand. The definition is what? It is a molecule. Ligands are molecule. It is a molecule. It can be an atom also. Molecule, atom, or ion, which are able to donate electron pair. Take care of this thing. I'm talking about electron pair, not electron. Which are able to donate electron pair to the central metal atom. Electron pair to the central metal atom or ion. Central metal atom or ion. These ligands, it can be neutral, it can be negatively charged, or it can be positively charged. All three possibility we have here. Now you see, one thing is very logical here. Since ligands donate a pair of electron to the metal, so what we can say, they are bonded with coordinate bond with the metal. How the coordinate bond forms? You know this coordinate bond, how this coordinate bond forms? Let me know if you know this, otherwise I'll explain it a bit. You know what is a coordinate bond, how it forms? Mass. Mass reply. What is a coordinate bond? Acha. So one example I'll take of coordinate bond. See, coordinate bond, what happens? Suppose you have, I'll take the example of NH3. Okay, NH3 has one lone pair of electron. So NH, H, H, and nitrogen has one lone pair on it. So generally what happens, the bond forms by the sharing of electrons. So here you see in this NH3, here we have one bond of hydrogen and one bond of nitrogen. Sharing takes place, this bond forms. So each atom in the bonding state, provides one electron to formation of bond. Correct? Here also you see one bond of hydrogen, one bond of nitrogen, one bond of hydrogen, one bond of nitrogen. So each of these atoms present in each bond contributes one electron in the bond. But what happens, suppose you have one H plus here, right? H plus here. H plus means what? This has one vacant s orbital, so it has ability to accept a pair of electron. Correct? And nitrogen has one lone pair available. Correct? So what happens here? This nitrogen has tendency to donate this lone pair of electron to this proton, which is H plus. Right? And what happens here? The bond forms between nitrogen and hydrogen, and we say nitrogen has 3 bond which is covalent, like this, N, H, H, and the 4th bond between this nitrogen and hydrogen is a coordinate bond directed towards the atom which accepts electron. So this bond is a coordinate bond, right? This bond is a coordinate bond. So what happens in this? The bond pair which is present in this bond, it originates from the single atom, that is nitrogen only. All these bond pairs, 2 bond pair of electron we have here, this pair of electron is of nitrogen only. But here in this bond you see one electron is of hydrogen, one of nitrogen, and that is same we have here also. But in this bond, the pair of electron which is present, that originates from nitrogen itself. There is no involve in like the electron of hydrogen does not involve in this bond formation. Correct? So this bond we call it as coordinate bond. This bond is coordinate bond, or the other name of coordinate bond, we also call it as dative bond. Dative bond. Got it? Point is, coordinate bond forms when the bond pair of electron originates from the single atom. Okay, one atom. This NH3, since it is donating electron, so here in this bonding state, this nitrogen will have positive charge on it. Hydrogen accepts electron, one positive charge, it becomes neutral and will have, and this is what we call it as NH4 plus, ammonium ion, NH4 plus. Got it? So the point is, this NH3 is electron pair donor we have. This is donor and this is acceptor. Did you understand this? H plus is the acceptor, NH3 is the donor. Understood? Bolo. Correct. So now the same situation we have here also. And the situation is what? Ligands donate a pair of electron and metal accepts pair of electron. Correct? Ligand donates a pair of electron and metal accepts a pair of electron. So you can replace this H plus by metal and you can replace this NH3 by ligand. So what we can say, the ligands attached with the central metal atom, with the central metal atom by what kind of bond we have here? What kind of bond? By coordinate bond, coordinate or dative bond. The third thing is this: the bond between the ligand and the metal is coordinate bond. Right? This is one thing. And third thing is what? Ligands are electron pair donor, and we know the donor electron pair donor are Lewis base, electron pair acceptor are Lewis acid. So what we can say here, the ligands act as act as a Lewis base, but metal act as a Lewis acid. Okay, Lewis base and Lewis acid. This question also they may ask you. Why? Because ligands are electron pair donor and metals are electron pair acceptor. Did you understand this? Correct. Now, next thing we are going to understand here, see, don't write this one now, just you look at it. Ligands are actually classified on two bases. One is the charge on it, charge on the ligand, and other one is the basis of denticity. Right? What is denticity? We'll discuss that. But charge means what? Like I said, ligands can be neutral, can be positively charged, can be negatively charged. All three possibility we have. So when we see the classification of ligands on the basis of charge, we'll have three types of ligand possible: negatively charged ligand, positively charged ligand, and neutral ligand. These are the three things. Charge also you should know that what is the charge present on the ligand, because later on we'll see we have to find out the oxidation number of metal in the given complex. Okay, we need to find out the oxidation number of metal, and to find out the oxidation number of metal you must have the information of the charge on the ligand, whether it is negatively charged, whether it is positively charged, whether it is neutral. All these information you should have. Then only you can find out the correct oxidation state of ligand. That's why this is important. Denticity means what? It is the number of electron pair accepted by a central metal atom from a particular ligand. Okay, so one ligand, if it can donate only one electron pair, its denticity is 1. We have possibility that one ligand can donate more than one pair of electron also, right? So depending upon the number of electron pair one ligand can donate, the classification of ligand we also have, right? If suppose ligand can donate only one pair of electron, then its denticity will be 1, and we call it as its monodentate ligand. Okay, denticity 1, monodentate ligand. Denticity 2, bidentate ligand. Denticity 3, tridentate ligand. Like that, we have classification of ligands. Okay, so did you understand the basis of classification of ligands? One is on the basis of charge, and other one is on the basis of denticity. What is denticity? It is the number of electron pair one ligand can donate. If it is 1, denticity is 1, called monodentate ligand. If it is 2, denticity is 2, called bidentate ligand, and so on. Is it clear? Yes. Okay. So next write down the classification of ligands. Classification of ligands. The first one, the first basis is on the basis of charge, write down. On the basis of charge. The first type we have here, A, is neutral ligand. Neutral ligand. The charge on this type of ligand is what? 0. So on neutral ligand, the charge is 0. And you should know the examples of this kind. The examples are, we have H2O, NH3, NO, we can have C6H6, etc. Okay, CO also we can write. One more example, carbonyl group, CO. Right. You see, since the ligands are electron pair donor, so obviously, what is the donor atom we have here in H2O? Can you tell me? What is the donor atom in H2O which donates electron pair to the metal? Oxygen, right? Because oxygen has lone pair of electron on it. Okay, so hence oxygen donates pair of electron, and with metal, this oxygen is bonded, not hydrogen. Similarly, nitrogen has lone pair of electron, so this is the donor atom here. In this, both can donate electron. C6H6, there is no lone pair onto it, but this pi electron can take part into bonding. Pi electron of it. We'll discuss this later. That also may form a coordinate bond. Pi electron of C6H6. Okay, so we'll discuss those later. All these are neutral ligand because there is no charge present on it. Okay. Second type you see, B, the second type we have negative ligand. Again, I am telling you, this charge you must remember because later on we have to find out the oxidation state of metal. For that, the charge is required. Negative ligand, which has negative charge on it. Right? So we have some negative charge on this ligand. For example, you see, we can have halide ion as the negative ligand. We can have NO2 minus, nitrite ion, SO4 2 minus, right? We can have Cn minus, negative ligand. We can have OH minus, negative ligand, etc. All these are negative ligand. Okay. Third one is positive ligand. Positive ligands are generally very less in number. Only one or two we have, that we'll see. Charge is positive. Plus charge we have on this ligand. Positive charge. For example, you see, we have hydrazinium ion, which is NH2, lone pair, NH3 plus. This is positive charge ligand. Nitrosonium ion, NO plus. This ion is nitrosonium. Very rarely we'll use this, but you write it down. And this one is hydrazinium. NH2 is hydrazine. So from that it is hydrazinium ion. Charge is positive one. Okay. So on the basis of charge we have seen the classification of ligand. The next one is on the basis of denticity. Classification on the basis of denticity. Okay. So first of all, write down the definition of denticity. What is denticity? What is denticity? Definition you write down. It is the number of electron pair it is the number of electron pair accepted by a central metal atom or ion from a particular ligand is known as the denticity of that ligand in the given complex. Number of electron pair accepted by the metal, that we have to see, which is the denticity. Okay. On the basis of denticity, the ligands are classified into following categories. See that the first type of ligand we have here is monodentate ligand. What is monodentate ligand? What is monodentate ligand? Tell me. Denticity 1. Okay, yes. Monodentate ligand, write down. The denticity of this ligand is 1. I'll write down the examples here. The examples of monodentate ligand are H2O. It can be neutral, it can be positive, it can be negative, anything. H2O, NH3, Cn minus, F minus, Cl minus, Br minus, X minus actually. CO, we have NO2 minus, OH minus, or NO, etc. All these are monodentate ligand, right? Remember here, this nitrogen and this oxygen both can donate electron. This nitrogen, this oxygen both can donate electron. But at a time, only one atom attached with the metal. That's why the denticity of these ligands is always one monodentate ligand. Second one, I write down bidentate ligand. Bidentate. We also call it as didentate. Bidentate ligand. Write down these are the ligands whose denticity is 2. Denticity is 2. Example, you see. I'll write down the next page. All of you have done this? Can I go to the next page? Okay. The first example we have of bidentate ligand is first example. These examples are also important. Even if more than one lone pair is, it donates only one pair. Yes, one atom can donate maximum one pair of electron, not more than that. Otherwise, that will be unstable, very unstable. Okay. One single atom present in a ligand cannot donate more than one pair of electron. Correct. Now you see the first example here we have is ethylene diamine. Ethylene diamine. Now you try to understand this carefully. The first thing is the structure of this ethylene diamine. Okay, and the structure will draw, and its symbol also you should know, right? Means ethylene diamine can be written as En also. So in the exam or question, you'll have this symbol written. They won't write all these entire name. They write this En simply. En means ethylene diamine. Correct? So this symbol also you have to memorize. A structure you can understand easily. Structure will be this ethylene diamine. So CH2 ethylene diamine we have, so two NH2 group attached here. Okay, so I am drawing the structure here also. This two nitrogen atom donates pair of electron to the metal. Okay, donor atoms are nitrogen here. Second example you see. B. Oxalate. Oxalate. OX. The symbol is OX. Okay. The structure is this. C double bond O, C double bond O, O minus, C double bond O, O minus. And this is the donor atom. Donor atom is these oxygens. Okay? C. Glycinate. Glycinate. The symbol is GLY. Glycinate. The structure will be CH2 N H H C single bond O minus double bond O. Right? Donor atoms are nitrogen here and oxygen here. Third one. Fourth one. Carbonate. CO3 2 minus. So the structure will be C double bond O, single bond O minus, O minus. Donor atoms are these oxygens. Dimethyl glyoxime. Dimethyl glyoxime. Short symbol is DMG. Dimethyl glyoxime. The symbol is DMG. And the structure is H3C C double bond N single bond O minus, and here we have CH3 double bond N OH here. Donor atom is these two nitrogen. DMG is this. Next one is dipyridyl. DYPYRIDYL. Dipyridyl. In short, we write it as DIPY. Dipyridyl, the structure is this. Two pyridine we have to attach together. Okay, this is one, this is another. Donor atoms are nitrogen. Dipyridyl is this. All these are bidentate ligand. Two donor atoms we have. Copy down the structure. We'll go to the next page. Mass. Where is mass? Done. Where is mass? Oh, you changed the name. Aditya. Okay. Next one. These three structures are important. One more thing I'll just forgot to tell you here. You see, when the donor atoms are same, right, the ligands are said to be symmetrical ligand. Okay. When the donor atoms are same, okay. When donor atoms are same, the ligands are said to be symmetrical ligand. Okay. So ethylene diamine, oxalate, glycinate is unsymmetrical, nitrogen and oxygen. But all these are symmetrical ligands. That also you keep in mind. Donor atoms are same, symmetrical ligand. Okay. Next one you see. The third one we have third type, which is tridentate ligand. Tridentate ligand means the ligand whose denticity is 3, 3 denticity. So we'll have 3 donor atoms here, correct? So first example here you see for tridentate ligand, the first example we have is diethylene triamine. First example, and in short we write it as DIEN, diethylene triamine. Okay, structure you can understand very easily. Diethylene group we have, right? So we'll write down 2 ethylene group, which is nothing but this CH2, CH2, and here we have one more CH2, CH2, 2 ethylene group, and with this ethylene group 3 amine group are attached. So NH2, this side we have NH2, and here also we have NH present. Okay, so donor atoms in this one is N. 1, 2, 3, 3 donor atoms we have. Correct? So diethylene triamine is this. Another example we have one more in this, that is terpyridine. Terpyridine. In short, we write it as TERPY. Terpyridine. Structure of terpyridine you see three pyridine we have here. Suppose this one. This is 3 pyridine. Okay, and all the nitrogen atoms are the donor atoms. This also donate to the metal, this also donate, and this also donate. Okay, terpyridine structure is this. We can say the donor atoms are same, symmetrical. Consider it would be symmetrical if it tridentate. See, symmetry in this coordination compound, we define the symmetry of ligand as per the donor atom. So if donor atoms are same, the ligand are said to be symmetrical ligand. Okay, structure we are not considering here. Got it? Likit, understood? Likit, understood? No family function. When is the next family function, Likit? Friday. Okay. Next one. Tridentate is this. So the next example, the next type we have tetradentate. Okay. Tetradentate ligand. tetradentate ligand. Okay. First example here, denticity is 4. Denticity is 4. And the first example here is nitriloacetate. Nitriloacetate. Nitriloacetate, the structure is this N. With this N, there are 3 acetate group attached. Acetate group is CH2, COO minus. One is this. Another one is again CH2, COO minus. And one more we have CH2, COO minus. Okay. Donor atom, if you see, the donor atom here is donor atom here is this oxygen is 1, this oxygen is 2, this oxygen is 3, and the fourth one is this nitrogen. All these are 4 donor atoms. Correct? Nitriloacetate. D. Triethylene tetraamine. Triethylene. 3 ethylene group will have in this, and 4 amine, tetramine. Okay, the symbol is TRIEN. There's no symbol for this one, nitriloacetate. This one is not important. Okay, the structure you see, triethylene. So one ethylene group is this, CH2 whole twice. This is one ethylene group, and with this 2 nitrogen attached of amine group N. This structure is not that tough. You can understand it easily. So one hydrogen will have like this, and with this nitrogen, we have the other 2 ethylene group attached. CH2, CH2 here also, whole twice. And with this carbon, there is NH2 group attached. Right? So hydrogen, NH2 I'll write like this. And with this carbon, there is another NH2 like this. So triethylene tetraamine, right? Donor atoms are what? Donor atoms are all the nitrogen. See, one is this, another one is this, next is this, and next is this. 4 donor atoms we have. Hence, the denticity is 4. Okay. Next one you see, 2 more we have in this. 2 more. Fifth one is pentadentate ligand. Pentadentate ligand. Denticity is 5. Okay. One example only we have here. And the example is ethylene diamine triacetate ion. Ethylene diamine triacetate ion. In short, we write it as EDTA 3 minus. Triacetate ion, EDTA 3 minus. Structure is ethylene diamine we have. So ethylene is this CH2 whole twice. ethylene. Diamine. Diamine means nitrogen attached with it. Nitrogen, nitrogen, and with this nitrogen we have three acetate ion attached. Okay, three acetate ion attached. So one is this CH2, C double bond O, O minus. One acetate ion is this. Another one is CH2, C uh, double bond O. I'll write on this side. Double bond O, O minus. Here we have one hydrogen because we have triacetate, two we have this side. So one we must have this side, which is CH2, C double bond O, O minus. Okay, and in all these you see what are the donor atoms? We have five donor atoms because density is 5. One is this, another one is this, 2, 3, 4, and fifth one is this oxygen, 5. So we have 5 donor atoms in this. Ethylene diamine triacetate ion. And the last one for this, we have the last one here, which is hexadentate ligand. Hexadentate ligand. Denticity is 6. Example is the same name we have here, ethylene diamine. Ethylene diamine tetraacetate ion. Tetraacetate ion. The symbol is EDTA. Tetraacetate we have, so 4 minus. EDTA 4 minus. The only difference in this case is what? You can write down the structure of this one. See, triacetate is this. If you replace this hydrogen by another acetate ion, the donor atom will be this oxygen, the next one. So 6 will be the denticity. Did you understand the structure here? You see the structure of this CH2 whole twice, nitrogen, nitrogen, CH2, C double bond O, O minus, CH2, C O minus, double bond O. Here we have CH2, C O minus, double bond O. And this, the last hydrogen, is also replaced by acetate ion, which is CH2, C single bond O minus, double bond O. Donor atoms are what? Donor atoms are 1, 2, 3, 4, 5, 6 donor atoms we have here. So these are the classification of ligands based on the charge and denticity. Okay. Symbol is important. Charge on the ligand is important because when we find out the oxidation state, we need charge of ligand over there. Okay. Can we move on next? Did you copy this? Okay. There are some different, The name of the ligands we have according to their nature and properties. 3, 4 different types of ligands we have that we'll see. The first type you write down here. Next types of ligand is flexidentate ligand. Flexidentate ligand. As the name suggests, its denticity is what? Denticity is flexible. Okay, flexible denticity we have. We miss the point simple if I tell you here. If one ligand has denticity 4, correct, it does not mean that when this ligand forms the complex, okay, its denticity will be 4 always. Structures of the ligands are not important. Why structure I have given you? Because you should know which one is symmetrical, which one is not symmetrical. Correct? So symmetry information you must have. Structure is not required. But if you look at the structure is not also difficult if you try to understand. Okay. Flexidentate ligand, like I said, its denticity is flexible. What I was discussing, suppose one ligand has denticity 4, and whenever this ligand forms a complex, it is not necessary that the denticity of the ligand in the complex will be 4. It cannot be more than 4 in any case. It can be 3, it can be 2, it can be 1, it can be 4 also. Right? So all polydentate ligands. Polydentate ligands means what? When the ligand's denticity is more than 1, if it is 2 or more than 2, right? It means what? If the ligand is polydentate, then it may behave as flexidentate ligand also, depending upon the complex. Again, I am telling you what? For a given denticity of ligand, it is not necessary that all donor atoms of one ligand donate electrons to the metal. Okay, if the denticity is 5, there are possibility that out of 5 donor atoms in the ligand, only 3 are donating electron, only 4 are donating electron. So if 3 atoms are donating electron, then the denticity of the ligand is 3 in that particular compound, but it is capable of donating 5 electron pairs. Maximum denticity is 5, but depending upon the molecule, its denticity can be 4, can be 3, can be 2. Understood my point? Is it clear or not? Flexidentate ligands, you see the name also suggests that its denticity is flexible depending upon the molecules. Am I clear? Tell me. लिखित बोलो. Okay. So now write down the definition into this. A polydentate ligand, I'll write down here also. A polydentate ligand is found to have different denticity in different compounds and they are known as flexidentate ligands. For example, you see, if I am writing down this ligand, EDTA 4 minus, what is the name of this ligand? What is the name of this ligand? It is ethylene diamine tetraacetate ion, because the charge is 4 minus. The last two ligand you see, if the charge is 3 minus, it is triacetate. If the charge is 4 minus, it is tetraacetate ion. Right? And what is the denticity of this ligand? Can you tell me the denticity? Denticity of this ligand is what? How it is 4? Likhit Shankar. How it is 4? Samyukta, Ardra, Aditya, how it is 4? Just now I have done it. Let's go through it once. EDTA 4 minus. What is the denticity of this ligand? If I write EDTA 4 minus, it is ethylene diamine tetraacetate ion, and its denticity will be 6, not 4. Why did you say 4? Because there are 4 negative charge. Is it? Tell me, Aditya, Samyukta. 4 minus charge we have because of 4 negative oxygen ion. But apart from 4 oxygen ion, we have 2 nitrogen also as a donor atom. Correct? So denticity of this is 6. Correct? Denticity is 6. But what I said for polydentate ligand means what? We are considering all those ligands whose denticity is 2 or greater than 2. Okay, no issue. Like it. So denticity is 6, but the point is this ligand whose denticity is 6, it may behave as a pentadentate ligand or tetradentate ligand or tridentate ligand, depending upon the structure of the structure of the complex basically. So denticity is 6, but it may behave as, it is possible that it may behave as it may behave as tetra, penta, dentate, etc. Tetra, petra, dentate ligand. That is possible. And this kind of ligands we call it as polydentate ligand. Sorry, flexidentate ligand. One example I'll give you here to make you understand what it means and how it happens. Suppose I am writing down this complex. You see this CONH3, CONH3, 4. Then we have CO3, close bracket, Br. This is the molecule we have. Okay. What is this CO? What is this CO? Cobalt, CMA, right? So CO is the central metal atom, right? This is CMA, central metal atom. What is this NH3? What is NH3? See, the central metal atom will always be the transition element. So cobalt is the transition element. Correct. What is NH3? NH3 is the ligand, right? Ligand. What is CO3? CO3 is a carbonate ion. It is also a ligand. So within the complex, we can have more than one ligand also present, more than one different types of ligand also present. Correct? It is not like always we have similar kind of ligand present in the complex. We can have two, three different kinds of ligand possible. Correct? These two are ligand. This is ionization spheres. That will let it be counter ion. Okay. Now, one information I am giving you here, and that we'll discuss later on also, like few minutes later, that this cobalt, you know, what is the atomic number of cobalt? Atomic number of cobalt is 27, correct? Right? And next noble gas configuration, if you see, which is krypton, and krypton, the atomic number is 36. Okay. Now you listen to me very carefully here. Cobalt has 27 electrons, correct? And it is accepting electron from the ligands. So it has tendency to gain this noble gas configuration, and that is why it is accepting electrons from the cobalt. Right? So when it accepts electron from the various ligands, the logic behind this is what? If this cobalt has 36 electron in the bonding state, it will be stable noble gas configuration, and hence it is accepting electrons. Correct? The point is it has tendency to gain this 36 electron. But now here, this cobalt does not have 27 electrons. And to understand how many electrons this cobalt has in this structure, we need to find out the oxidation state of this cobalt. Can you tell me the oxidation state of cobalt in this molecule? Oxidation state of cobalt? Tell me, guys, what is the oxidation state of cobalt? How do we do this? You see, Br minus we have, correct? Br minus. So on whole this complex will have plus one charge, right? Plus one charge. And you see this NH3, like I told you, you should know the charge on the ligand. NH3 is neutral, so we'll have zero charge on this. Correct? CO3 is the carbonate ion, right? So it has minus 2 charge on it. C double bond O, single bond O minus, O minus. Yeah, I think 3 is right. So minus 2 charge on this carbonate ion, 0 on this NH3, minus 2 will go this side, plus 3. Plus 3 is the oxidation state of cobalt. ठीक है? Understood? Where is Hamsini? Hamsini just wrote her name in the beginning, and then I don't know where she is. And then she left, I guess. Hamsini is not there. Yes means what? Hamsini left. That's what you mean. Or this is plus 3. Acha, she is studying bio. Paras is assuming something.
Okay, fine, fine. Hamsini is there. Okay, okay. Yeah, yeah, yeah. I understood, Hamsini. I am sorry. I am sorry, and Paras, you should apologize to Hamsini. Okay. Paras, apologize, no? Ah, that's better. अब ठीक है.
Okay, now you see what I was trying to explain here. The oxidation state is +3, correct? So you see the cobalt initially has 27 electron. When you write down CO plus 3, it means this cobalt has 24 electron present um, in this ion, correct? 24 electron presence. And to gain this 36 electron or inert gas configuration, it requires 12 more electron. Is it right? Okay, 12 more electron it requires. So from where this 12 electron this cobalt ion gains? This 12 electron it gains from the ligand with which it is attached, because we know the ligands are electron pair donor. So how many electrons or how many donor atoms we require so that we'll get 12 total electron to this cobalt? You understood my question? Cobalt CO3 plus requires 12 electron to gain this configuration, right? So we must have 6 ligands if it is monodentate, or in other way we can say we must have 6 donor atoms which is getting bonded with this cobalt ion, correct? To get 12 total electrons, cobalt must attached with 6 donor atoms of the ligand. Is it clear? So now you see, first of all here, this NH3 is the monodentate ligand or bidentate ligand? Tell me. NH3 is monodentate or bidentate? NH3 monodentate or bidentate? Yeah, it's monodentate ligand. Okay, so first of all, what we should know, it is monodentate ligand, correct? And this one is carbonate ion. It is bidentate ligand. Yes or no? Bidentate ligand, correct? So far, what we have discussed, this CO3 plus requires 12 electron, right? Now you see four monodentate ligand we have written inside this square bracket. It means this nitrogen and this cobalt are attached. Correct? So this 4 monodentate ligand donates 8 pair of electron, sorry, total 8 electron, 4 pair of electrons, and this bidentate which has 2 oxygen atom as a donor atom. So here the both oxygen atom donates electron pair to this cobalt, and hence the cobalt will have this 12 electron, and hence the bonding completes. Did you understand this? Did you understand this? See, NH3 is monodentate. So how many electrons this NH3 donates? One NH3 can donate one pair. 4 NH3 we have. So total 8 electrons it donates. And from where the other 4 electrons this CO3 plus get? The other 4 electrons it get from this ligand which has 2 donor atoms. So if I say that both of this oxygen atom is donating electron to this cobalt, is it right? Is it right if I say both oxygen atom of carbonate ion donating electron to cobalt to form the stable complex? Tell me, is it right? Correct. So point is, two donor atoms, two oxygen are donating electron, right? That's why this is bidentate here. Since two oxygen atom is donating electron, that's why it is bidentate. Okay. For nitrogen, which is monodentate ligand, if it is written inside the square bracket, it means it is attached with this metal. Right? So we have to consider all four nitrogen atom here. Correct? Now, this you understood. Similarly, if I write down one more molecule here, you see this one. Just one change will do in this. Compare this one, CONH3, 5. Instead of 4, I'll write down 5 here. CO3, close bracket. Okay, this is again carbonate and Br this side. Everything is same. Even the oxidation state is also same here. That is +3. Means for this molecule also, this cobalt requires 12 electron to get inert gas configuration. But again, this NH3 is monodentate, and this has capacity to donate 2 pair of electron because it is bidentate ligand. The maximum capacity is what? The maximum density is 2 for this carbonate ion. But how many electrons this NH3 is donating to this cobalt? Can you tell me how many electrons this NH3 is donating to the cobalt ion? Ten. Is it clear, all of you? 10. NH3 will have 5 NH3 molecule. So this will donate 10 electrons. Now, next thing, how many electrons this CO3 plus further requires to get inert gas configuration? 10 electrons it gains from NH3. Then how many electrons it requires more? Two more electron it requires. Yes. Understood, all of you? Two more electrons it requires. Correct. So two more electrons this CO3 plus requires, and from where this 2 electron this CO3 plus gets? It gets from the other ligand, which is CO3. But CO3 has capability of donating 4 electron pairs in total, if you see, because density is 2. Right? So out of the 2 oxygen atom here, only 1 oxygen atom donates electron pair to this cobalt. So in this molecule, this CO3 ligand is also a monodentate ligand. It has capability to donate 2 pair, but this CO3 plus requires only 2 electron, only 1 pair of electron. That is why only 1 oxygen atom donates its electron to this metal, and hence it is behaving here as monodentate ligand, not bidentate ligand. However, it has maximum capacity to donate 2 pair of electron. Since it is donating only 1 pair, hence it is monodentate in this compound. How many of you understood this? CLR. Yes, according to the requirement. So one thing again I'll tell you here, you must be thinking that why not this 4 NH3 molecule donates 8 electron, and why not this 2 oxygen donates 1 electron pair to this? Means 4 NH3 like they are doing here, and 2 from this 2 oxygen atom. This is what the doubt you have. The other oxygen, Shreya, it will be there as it is. It won't take part in bonding with the metal. Right? The other oxygen atom will be there, but it won't donate electron to the metal. It will be there in the complex, but won't take part in bonding with the metal. Correct? So if you have doubt here, that why not 4 NH3 and 2 oxygen atom of CO3 involves? That cannot possible here. That is not possible here. Because when any monodentate ligand is written inside the complex, okay, it means it is bonded with it. Otherwise, there is no point writing down their 5NH3 molecule. Did you understand my point? We cannot take here 4 out of 5 NH3. We cannot assume 4 out of 5 NH3 here because it is written inside the square bracket. If it is written, it is attached. So we have to consider all monodentate ligand attached with this cobalt. Further, this CO3 required this CO requires only one pair which comes from this CO3 molecule. So this CO3 also attached with this cobalt, but with only one oxygen, not with the both the oxygen. Is it clear? All of you understood, right? CLR, if you understood, all of you. Correct. So the point is, this is the one example of flexidentate ligand. Like this only, any polydentate ligand. Polydentate ligand means what? Its denticity must be 2 or more than 2. Any polydentate ligand may behave as, flexidentate ligand depending upon the structure or the molecular formula of the complex. Correct? This is what flexidentate ligand we have. Correct? Next one you write down. Another type of ligand is chelating ligand. Write down next type CHE CHELATING, chelating ligand. Definition you write down. All polydentate ligands, all polydentate ligands are chelating ligands if on coordination it results in the formation of a closed or cyclic ring. Closed or cyclic ring. Closed structure we get. Okay. Next line you write down in this. The complexes forms in this way. The complexes forms in this way. Are called chelates. These chelates are comparatively more stable than the ordinary complex. Okay. One thing is what, when the donation of electron pair takes place, there are tendency to form a cyclic ring. For example, suppose if I have this, suppose we have carbonate ion. Carbonate ion is this. when both carbonate ion, when both oxygen atom here takes part in bonding, right? Metal we have here. When this oxygen donates electron to the metal, so you see we are getting a cyclic ring, four-member cyclic ring compound. So this cyclic ring we call it as chelates. Okay, and because of its cyclic structure only, it is normally more stable than the ordinary complex. Ordinary complex means what? When we have simple compound, we'll get, there is no cyclic ring we get over there. In that case, it is more stable normally, right? Chelates are more stable than ordinary complex, but we have one exception in this. Exception is what? When we get three-membered ring, exception, write down. Write down, in case of three-membered ring, three-member ring, the chelates are less stable. Right? Three-member ring are generally less stable because of large angular strain, and that's why chelates are also less stable. For example, you see hydrazine NH2. When NH2 behaves as a ligand, it donates electron pair to the metal and forms a three-membered ring. Hence, this one is less stable than the ordinary chelates. Is it clear? Is it clear? Tell me. Okay. What? What? Why does happen? Paras, tell me what happened. Three-member ring less stable because of angular strain. Any three-member ring is lesser stable than four-member, five-member, like that. Okay, angular strain is more over there. No, the bond angle is 120, but the hybridization of carbon atom over there is sp3. It should be 109 degrees. So the angular strain is what? Angular strain is 109 minus 20. Sorry, 60 is the bond angle over there. So any smaller member ring is lesser stable than the larger member ring. Four-member ring is more stable than third. Five-member ring is more stable than fourth, like that. आया समझ में? Correct. So the next one you see ambidentate ligand. Next page. We'll take a break after this. Ambidentate ligand. Hamsini, you want break? Huh? Pizza. Likhit always wants pizza. Okay, लिखित पिज्जा मिलेगा, दुखी नहीं होना है. Okay, ambidentate ligand. Write down these ligands. These are the ligands which has these are the ligands which has more than one donor atom available, but in forming complex only one donor atom is attached to the metal ion. With example, you will understand. You see this example. Suppose I write down Cn minus. Okay. C triple bond N minus, and carbon has one lone pair. If you see this, carbon has lone pair, so it can donate. Carbon is a donor atom. At the same time, nitrogen also has tendency to donate electron because it also has one lone pair on it. So this also may donate. So carbon, nitrogen, two donor atoms we have over here. So that's why we call it as ambidentate ligand. The name of this, when carbon donates electron, we call it as cyno, and this one is isocyano. Okay. Similarly, another example you see, NO2 minus. NO2 minus, the structure is this: N double bond O, single bond O minus. Nitrogen has lone pair, can donate electron, and oxygen at the same time also has tendency to donate electron. Negative charge has tendency to donate electron. Oxygen. So again, you see two donor atoms we have here. This is also ambidentate ligand, which is NO2 minus. This is nothing but NO2 minus. This is Cn minus. When nitrogen donates electron, we write it as nitrato N. When oxygen donates electron, it is nitrato O. If in the complex all ambidentate ligands are monodentate. Okay, ambidentate. No, you see this one? Yeah, in the complex it will be monodentate. In the complex, only one atom donates electron. So while forming complex, it behaves as monodentate ligand only, but the ligand has more than one donor atom available in its formula, molecular formula or ion, whatever it is. Because it is behaving as a monodentate ligand in the complex. Okay, when in the question when NO2 is written, it means nitrogen is a donor atom. But if it is written like this ONO, it means oxygen is a donor atom. Understood this? Is it clear? Another example you see, one more example. If you have this one, O, C, triple bond N, negative charge. When oxygen is donating electron, we call it as cynato O. NaTO. Cynato, NaTO it is. Cynato O when oxygen is donating electron. But when nitrogen is donating electron, like this, O, C, triple bond N, lone pair on this nitrogen donating electron, negative charge. This we call it as cynato NATO, cynato N. This is what the ambidentate ligand we have. Okay, more than one donor atom is present, but while forming the complex, only one atom attached with the metal. Hence, all ambidentate ligand behaves as monodentate ligand. Okay, so we'll take a break here, and after that we'll see one more terms, and then few questions we'll discuss onto this. Okay, so take a break now. It's 6:23, 6:25. So we'll start the class at what time? Tell me. 6:45 p.m. will resume. 7:15 you can come, Aditya. ठीक है 6:45. Okay, guys, can we start? Okay. The next term you write down is coordination number. Coordination number. Write down. It is the number of atoms of ligand. It is the number of atoms of ligands that are directly attached directly attached to the central metal atom or ion by coordinate bond. Utkarsh, which batch, Utkarsh? Which class you are in? Okay, I'll do that. By the way, which class you are in, Utkarsh? Okay, class 10th. You are already taking class in Centum, right? Utkarsh, do you have contact of Tushar sir or like Tushar sir contact you have? I did not get any messages. Do you have my number? I did not get any message from your side. Acha, you do one thing. I'm taking class right now. Just drop your number here. I'll just do that. I did not get your messages. You drop your number here. I'll do that. Okay. I'm taking class right now. Or you can text me on this. Text me on this, Utkarsh. Okay, so the coordination number is the number of atoms of ligands that are directly attached to the central metal atom or ion by coordinate bond. Okay, for example, you see, if I write down this molecule, this complex, which is CuNH3, CuNH3 4, and we have 2 plus charge over here. What is the coordination number for this molecule? And then CuNH3, I'm sorry, the another molecule is this CuEn whole thrice, and then 3 plus. 3 plus. We need to find out the coordination number. Coordination number of metal will find out all this. Okay, coordination number of metal. So first of all, you see this means what? If you try to understand the structure of CuNS3 whole 4, we have copper, right? We have copper present at the center, and the 4NH3 molecule surrounds the copper like this. And all these nitrogen atom donates a pair of electron to this copper, forms a coordinate bond. Is this right? So the number of atom which is attached to the number of atoms of ligands attached directly to the copper or the metal is 4. Hence the coordination number is what? Coordination number is 4 for this molecule. Okay. Understood this? Did you understood? Tell me. Correct. Now, what is the coordination number of this? The second one? For the second one, the coordination number is what? Second one. Tell me the answer. Is it 3? 6. Denticity is 2. Yeah, you see this En is ethylene diamine. Okay, if you look at the structure of this complex, it will be, I forgot to write the charge on this, which is 2 plus. The structure of this copper will be here in the center, and ethylene diamine is nothing but this NH2. This is one ethylene diamine, and like this we have 2 more. Right? So if you see the number of atom which attach with this metal, this is 1, 2, 3, 4, 5, and 6. This is the structure we have. Ethylene diamine, the denticity is 2. That's why 2 atom is donating electron here. And we have to count all these atoms. So coordination number is 6 in this one. So basically with these two examples, if you try to write down the formula of coordination number, it is the number of ligands present into the denticity of ligand. Number of ligand into the denticity of ligand in the molecule. Right? Denticity of ligand in the molecule. Right? But you have to be a bit careful over here, because when you look at this example that we did here for this flexidentate ligand, this one you see, if for this, if you find out the coordination number, it will be 4 plus 2, 6. Correct? But here it will be 5 plus 1, because here it is monodentate ligand. Right? So if you calculate according to the denticity, 5 into 1 plus 2 into 1, if you see, you're getting 7 over here, which is not possible. More than 6 coordination number you won't get. Okay, more than 6 coordination number you won't get. Coordination number 6 is the most important compound we have for this chapter, right? So here you must take care of. However, the denticity of CO3 is 2, but in this complex, it is monodentate ligand, so we count 1 for this. Bidentate ligand will count 2 for this. You take care of this thing. Okay, is it clear? So we use this formula, coordination number into denticity. Denticity of what? Denticity of ligand in the complex. Okay, that is the exact formula we have. Okay, next thing we have to discuss here is the bonding of this coordination compound. Okay, and for that, the one first theory, which the first theory given for this bonding of coordination compound, we call it as Sedgwick EAN rule. EAN rule. This EAN stands for effective atomic number. EAN stands for effective atomic number. Okay, write down here. This stands for effective atomic number. Effective atomic number. Write down. Write down to this. According to this rule given by Sedgwick, it is the name of the scientist. Okay. Utkarsh, it is 12th class going on. No, it is not possible, Astrea. Even coordination number 7, it's not. It is not in our syllabus. Maximum you'll get till coordination number 6. Utkarsh, this is not for you. This is not 10th grade. It is 12th grade. Okay, effective. Write down. According to the metal. Sorry, according to this rule. According to this rule, the metal or metal ion in a complex tends to acquire noble gas configuration by gaining electron from ligands. Okay, so basic point is what? Metals and metal ions tends to acquire noble gas configuration that we discussed in flexidentate ligand. Okay, the same thing we have here, tends to acquire noble gas configuration by gaining electrons from ligands. One thing here, it is what? This rule fails in many cases. This rule fails in many cases and works best for the metals with low oxidation state. This was the first attempt to explain the bonding in coordination complex. However, like we already did in chemical bonding, there are many different theories. Lewis dot structure we have VBT valence bond theory, we have MOT molecular orbital theory. Similarly, here also there are many different theories for coordination complex, bonding in coordination complex. This was the first theory, and what it says that metal ions has tendency to gain the next higher noble gas configuration by gaining electrons from the ligands. However, this is not true for different gases, different complexes. Correct? So for example, you see, if you have to find out the effective atomic number is what? See, effective atomic number EAN is actually the total number of electrons, or the net number of electrons of the metal or metal ion of the metal in complex, the complex in which the metal is present. What is the total number of electron we have? That we'll see. I'll discuss that, Shreya. Just give me 2 minutes. Okay. See, effective atomic number. First of all, you see this, you will understand. Effective atomic number, the formula I am giving you here, it is equals to the atomic number minus number of electrons loses in the formation of ions, and number of electrons will write with sign here. So basically it is oxidation state with sign. I'll just in the simple language, if I write here, this is the oxidation state with sign you'll write down here. Or instead of this, you can write down oxidation state with sign. Means if it is +3, write down +3. -3, write down -3. This or this. Plus the number of electrons accepts from ligand. It's very simple and straight formula it is. You see, effective atomic number means what? Net number of electron, total number of electron the metal has in bonding state. Okay. So first of all, atomic number minus oxidation state. Oxidation state, if it is positive, it means it loses electron. So atomic number minus the number of electron loses plus the number of electron gains. So it is actually the formula of total number of electron. Did you understand this in a bonding state? Did you understand this in the bonding? This formula, did you understand? Atomic number minus the number of electron lost in forming oxidation state, that is plus if it is there, plus the number of electrons gains. Clear? Tell me guys, did you understand this? Yeah, this is the formula we have. Now you see, how do we find out the effective atomic number of various molecules? Here you will understand how it was, discussed in case of flexi-dentate ligand. Okay. First example, you see, we have K4FeCN6. We need to find out the effective atomic number for this complex EAN. Okay. So first of all, tell me, what is the oxidation state of ion here? What is the oxidation state of this ion? K4, K plus, so it is -4, -1 on this cyanide group, so -6 this side, so it is +2. Is it clear? +2 oxidation state. Correct? Now, effective atomic number we have to find out. We'll use the formula. First of all, we'll write down the atomic number, that is 26, minus oxidation state with sign, that is +2, plus the number of electron accepts from the ligand. So ligand has 6 monodentate, so 6 into 2. What is this value? 6 into 2, 12, 12 plus 26, 38, 38 minus 2, 36. You see, this 36 is the atomic number of krypton, and it means what? In this state, it gains noble gas configuration, hence it is stable. This is the effective atomic number. Understood this? Understood this, guys? Effective atomic number is 36, and that is why it is stable. That's what the Sedgwick EAN rule we have. The metal ions has tendency to gain the next higher noble gas configuration by gaining electron from ligand. That's what it means. Now you see the another example here. FeCO5. Tell me the effective atomic number EAN for this FeCO5. Third one, CrCO6. Effective atomic number. What is the value you are getting? MnCO5. Here, what is the number you are getting? Effective atomic number. See, CO carbonyl group is neutral ligand, 0. Right? So oxidation state of ion is also 0. So this will be 26 minus 0 plus 5 into 2. 36. Here also it is 0. So effective atomic number is what? Chromium is 24 minus 0 plus 2 into 6, 36. Again it is stable. What is for this MnCO5 you are getting? For MnCO5, if you calculate effective atomic number, EAN, this is again 0. So it is 25 plus 0 minus 0 plus 2 into 5 is equals to 10, which is nothing but 35. You're getting 35 here. Are you getting 35? Yeah. So what happens in this, since it is not gaining the inert gas configuration, so this molecule dimerizes, right? MnCO4 actually dimerizes and it exists in this form, Mn2CO10. This dimerizes and it exists in this form. Now in this form, if I try to find out the effective atomic number, you see what happens here. Bonding here, you see Mn and Mn are attached with each other, and with this there are 5 ligands attached with each Mn manganese atom here. 5 here, 1, 2, 3, 4, and 5. Correct? So in this one you see what happens. All these 5 ligands, CO, 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 each of these ligands donates 2 electron. Correct? So 5 into 2, 10 electron we have here. This is 1 electron for this manganese, and this is the another electron for this manganese. So if you calculate the effective atomic number for one manganese here, that will be what? 25 is the atomic number of this manganese, plus I'm not using that formula. It is different. Okay? That formula I'm not using. I'm just trying to calculate in this bonding state, which is a dimer form of this MnCO5, what is the total number of electron this manganese has, each of these manganese has. So 25 is the atomic number of this, 10 electron donated from each of this ligand, plus, you see when I say 25, I am counting this electron of this manganese, correct? But this electron I am not counting, which is of this manganese atom, right? So for this electron, we have to add 1 over here, and that's why this becomes 36. Same will be for this manganese, and hence the effective atomic number for Mn2CO10 is 36, which is the inert gas configuration. That is why MnCO5 dimerize, and it exists in this form, not in this form. Did you understand this? Is it clear? Any doubt? Let me know, guys. All of you understood quickly. Tell me fast. Correct. So this actually, this effective atomic number or Sedgwick rule is valid only for few kinds of metal. Metal which has carbonyl group as the ligand. Mainly for those compounds only it is valid. In general, right? There is no rule for this. But in general, the metal which contains carbonyl group as the ligand, for those where it is 10. 10 electron because we have 5 ligands. No, 1, 2, 3, 4, 5. Each ligand donates how many? 2. So 5 into 2, 10. Yes? Sure, tell me. Correct. Now, you see, the last part for today we'll discuss is the application of EAN rule. Just 2, 3 examples we'll see. Application. See, there are two applications for this. One, we can find out coordination number to find out coordination number. And second one, we can also have the idea of reducing an oxidizing behavior. Reducing or oxidizing behavior. Right? Like I said, this rule is valid mainly for the metal low oxidation state or with carbonyl ligands. Okay. So this one you see, if you have this molecule and if I ask you what is the value of X in this, find the value of X. Second one, in this also find the value of X. X is nothing but the coordination number we'll have here. Third one, MnCO6. MnCO6, effective atomic number for this. And the last one for today is VCO6, effective atomic number for last two. You see, FeCO6, according to EAN rule, what we know that the effective atomic number is equals to 36, the next higher configuration. Correct? Now for this it is 0, here also it is 0, here also it is 0, here also it is 0, the oxidation state, because this is neutral ligand, CO. Okay? So iron has 26 atomic number, minus 0, there is no oxidation state, plus one of this ligands gives 2 electrons, so X gives 2X. X value if you find out, that will be equals to 5 here. So coordination number is 5 in this. Did you understand this one? Tell me. समझ में आई बात? What is the coordination number of second one? X value is what? X value. Can you tell me? I'll write down the answer here. Tell me the answer. Four. Yes. X value is 4. Coordination number is 4. All of you got this? X value 4. Any doubt? Let me know. Are you getting 4? All of you? Correct. MnCO6, what is the effective atomic number for this? Tell me. MnCO6 and VCO6, what is the effective atomic number? EAN for this will be, and EAN for this will be. What is the effective atomic number here? $37. All of you are getting 37? Okay. Effective atomic number is 37. So since it has one more electron than the inert gas configuration, so this molecule has tendency to lose one electron. MnCO6 with one positive charge plus one electron. And in this state, the effective atomic number, if you calculate, obviously one electron it has lost, so it is 36. Right? So you see, this is nothing but the oxidizing nature of this. This is getting oxidized, right? Losing one electron, and hence it is behaving as what? This molecule has tendency to lose one electron to gain inert gas configuration. So this molecule is behaving as reducing agent. Is it clear? This molecule has 37 electrons, so it has tendency to lose one electron to gain 36 inert gas configuration. It means it is behaving as a reducing agent. Fine. Okay. What is the effective atomic number here? You'll get here 35. Yes or no? (35) means to gain 36 electron, it has tendency to accept one electron and forms VCO6, one negative charge on this. Means it is getting reduced. It means this molecule is behaving as what? Oxidizing agent. Any doubt? Understood, all of you? Okay, so this is the two application of EA acidic EN rule we have. That is to find out our coordination number and reducing oxidizing behavior. Okay, however, this rule is valid only for few molecules. Generally, the complexes which has CO as the ligand. Mainly for those only it is valid. MnCO5 may behave as an oxidizing agent, fine, but it is not stable in that form because of 35 electrons. When you take MnCA5 and if you want to understand whether it is behaving as reducing and oxidizing agent, obviously it is an oxidizing agent. Correct. But since 35 is not a stable configuration, and that is why it gets dimerized and forms stable configuration. Okay. MnCO5 manganese has very odd structures. Okay, that kind of dimerization is very less tendency will have in this vanadium carbonyl compound that you have. Okay, so even that's the thing. So you won't get any different question to this. They only ask you to find out like this X or oxidizing and reducing behavior. Fine. So we'll wind up the class here. Next class we'll start with nomenclature in coordination compound, and then we'll see the other bonding theory.
Okay, any doubt? And why should I? Okay. Any doubt, guys? Okay. Chalo, see you in the next class. Bye. Thank you. All the best for your exam tomorrow.